Okay, so in this video we're going to start doing some definite integrals, not necessarily getting quite into the fundamental theorem of calculus yet, just sort of a general idea of how definite integrals work. First question, we want to suppose that, okay, the integral from 0 to 4 f of x dx equals 6, integral from 0 to 4 g of x dx equals negative 3, and the integral from 0 to 8 f of x dx equals 11. So we want to find some various things here. This is just generally properties of integrals. So the first one, we've got this 0 to 4, 3 times f of x dx. Well, it's the same as this integral that equals 6, except there's this 3 here. So there's a general property, which means when I have a constant multiplied by a function inside an integral, I can pull that constant out. So this is 3 times the integral from 0 to 4, f of x dx. Now we don't know what f is, but we know the integral from 0 to 4 of f dx is 6. So this just works out to be 3 times 6, or 18. Next one, we've got 2 times f of x minus 4 times g of x. We can use the same thing as before. We're going to use the fact that definite integrals are linear, I suppose. So this is going to be, well, let's just do it a couple steps. First thing I can do, 2 times f of x dx minus the integral 0 to 4 for g of x dx. So I can split up this difference into the difference of two different definite integrals. And then I can pull the constants out in front. So this is 2 times integral 0 to 4 f of x dx. And I can pull the 4 out, 4 times integral from 0 to 4 g of x dx. Here. Now, a lot of times I would skip straight to this second step. I mean, I can kind of see it's 2 times f of x minus 4 times g of x. Here, I sort of showed another step there. In any case, this integral 0 to 4 f of x dx is 6. And the minus 4 times the integral from 0 to 4 g of x dx works out to be negative 3. So this is 12 plus 12. We get an answer of 24. Next up, we're going to integrate from 4 to 8, 5 times f of x dx. Now, what we have for f, let's just go back up here to look at this. We have an integral from 0 to 4 and an integral from 0 to 8 here. So what we're going to do here is there's a property here where essentially what I can do is I can say an integral from a to b, let's just how about use h of x dx, plus an integral from b to c, h of x dx. That's the integral from a to c, h of x dx. In essence, what we're saying here is that if I have an a b, and a c, and I've got some function here, y equals h of x, if I take the area under the curve from a to b, maybe we'll shade that in red, and then from b to c, I take the area under the curve, that if I go from a to c, I just add the red area plus the green area. So a fairly sort of intuitive geometric idea here. Now, we've got something that looks kind of like that here, but we really have this b to c part. And so what we're going to get here, let's just write it this way. Let's do an integral from, let's see, we want to have 0 to 4. Now, I'm going to do a 5 f of x dx plus an integral from 4 to 8, 5 f of x dx. That should equal an integral from 0 to 8, 5 f of x dx. And the thing we want, let's do that in green, is this thing here. So we need to figure out these other two, but we're effectively given those. So the integral from 0 to 4, well, let's do it this way. This is 5 times the integral of 0 to 4, f of x dx, plus the integral 4 to 8. I'm going to leave the 5 in here. It's just sort of what we're looking for. And then this is going to be 5. I can pull this one out. And I have really this integral from 0 to 8 and 0 to 4. 0 to 4 gives me 6. 0 to 8 on f gives me 11. So this is 5 times 6 plus the thing we're actually looking for equals 5 times this other integral is 11, and that tells me the integral from 4 to 8, 5 times f of x dx, should be 5 times 11, that's 55, and then I subtract 5 times 6 is 30. That gives me a 25. We can kind of piece this together a bit. Here's another one. We're going to do an integral 0 to 4 f of x minus g of x over 6 dx. So first thing here is this order of integration is sort of backwards. It's going from big to small. There's a rule of integrals that says I can switch that order, and then I just get negative of what's inside. Or, probably more likely, I'll put a negative out in front here. So I can swap the 0 and 4, but that introduces a negative. In essence, what I'm doing here, like why that should be true, let me draw this up in green, is that I'm doing sort of a Riemann sum here, and my delta x, maybe this distance here, that's delta x. Generally, we'd think about that as sort of the right minus the left, but when we go sort of the other direction, we're effectively doing, whoops, left minus right is what we're doing. So you're doing that, and that's actually a negative of left minus right. In some sense, you could trace this through and then sort of explain why this negative pops up. Okay, so in any case, I can now write this as negative integral 0 to 4 f of x dx. So I can use the negative there, and then the negative times the negative gives me a plus. The 6 out in front, and the denominator I can bring out in front, 1/6, 0 to 4 g of x dx. And then I just go to the initial problem. I look up these two integrals here. Just box those up. Well, it didn't box very well. So that integral and that integral should be given. So the integral 0 to 4 of f and integral 0 to 4 of g. So 0 to 4 of f is 6. G gives me negative 3. So I get a negative 6 plus 1/6 times negative 3. That's negative 6 minus 3/6, which is a half. So that's going to be negative 12 halves minus 1/2. That's negative 13 halves. Okay. Next question. We're going to sort of use the Riemann sum definition of definite integral to evaluate. When it says use the Riemann sum definition, what we're talking about here is not using the fundamental theorem of calculus, which would involve antiderivatives. So we're going to sort of do this the long way here. So what we're going to do is we have x squared minus 3 from 2 to 7. And we're going to split this, well, let's just draw it. So x squared minus 3 at 2, let's see, I'm at 1. Let's go here. So I don't actually care what the function looks like, to be honest. It's a parabola. Maybe it does this. I don't know where that middle point is. Well, it should be square root of 3. That's less than 2. So we're actually strictly increasing here. Not that it's actually going to matter. But I'm really trying to find the area under this curve. And to do that, what I'm going to do is split this into really n rectangles. So I think of these as rectangles. And then I just have to have the height somewhere sort of in that interval, function value in that interval. It doesn't actually matter where, because we'll take the limit as the number of rectangles goes to infinity, and sort of any point I pick in the interval will end up being equivalent once I take that limit. So what I'm going to actually do is I'm going to take right endpoints here, just because I think that works out a little bit easier. So I'm actually going to take, sort of drew my picture, I guess incorrectly. I should be taking the right endpoints is what I'm going to do here. Okay, so we need some things here. We need to have a delta x. So if we're going to do n rectangles. So the distance, sort of the width of one of these rectangles, well, it's 7 minus 2. It's a distance 5, and I just divide that by n. So delta x is 5 over n. And then xk, those are sort of the points where I'm finding the heights, really the function value. So I was going to choose right endpoints. The reason I want to do that is that allows me to write xk as 2, sort of the initial left endpoint, and then just add k times delta x, which is 2 plus, well then, delta x is 5 over n, so I get plus 5k over n. And then this works for k equals 1 to n here. You could have used left endpoints, and this would be k equals 0 to n minus 1. Somehow I feel like this right endpoint just feels a little more natural here, but it's not really a big deal. You could also use midpoints, but that's going to get a little bit uglier in this sort of calculation. Okay, so that's delta x, or that's xk. And then we're going to need f of xk, function value at xk. Well, that's x squared minus 3. Well, xk squared minus 3. So it's 2 plus 5k and squared minus 3. If you work that out, you do the square, I get 4 plus, so it's going to be 20k over n plus 25k squared over n squared minus 3. 4 minus 3 is 1. That's 1 plus 20k over n plus 25k squared over n squared. So there's my f. So I sort of set this up. And now my definite integral, and this is sort of how things are really defined, is this is actually a limit as n goes to infinity of really the sum of the areas of really the n rectangles. So the way I'm going to do that, I'm going to do summation k equals 1 to n rectangles. I'm going to do the height of the rectangle, that's this f of xk. So this is 1 plus 20k over n plus 25k squared over n squared. So that's f of xk. And then I'm going to multiply by delta x, which is 5 over n. Okay, and then we just need to work this out. Limit as n goes to infinity. I can pull the 5 over n outside of the summation. And then I get a bunch of different summations. So the 1, I get a summation k equals 1 to n of just 1. Plus this 20k over n. I can pull the 20 over n outside of the summation, the sigma, and get a summation k equals 1 to n of k. And I can do a similar thing with the 25k squared over n squared. Pull the part out that doesn't have a k here, and then I get a k squared. So I do that, and then I'm going to use my formulas for summations k equals 1 to n of 1 and k squared. So this is 5 over n. Let's write that a little bit more nicely. 5 over n. Okay, if I do summation 1 to n of 1, that's 1 plus 1 plus 1 plus 1 n times. That's just n. Summation formula for k equals 1 to n of k, that's n times n plus 1 over 2. That's just a formula that I have sort of memorized or maybe look up. And then there's a similar formula with the k squareds. That's n times n plus 1 times 2n plus 1 over 6. Here. And now we got rid of the summation, so we just have to do some algebra. And then take the limit eventually. And so I'm going to distribute, well, let's maybe before we distribute the 5 over n, let's simplify the inside. So n plus, these n's cancel. The 2 and the 20 cancel with the 10, so that'll give me a 10n plus 10. You can cancel that n with one of those n's. And I'm going to get, let's see, 25 over 6. There's nothing that simplifies there. Times, let's see, I'm going to get, well, how about 25 over 6n? I can keep the n. I'm going to get 2n squared plus 2n plus n. That's plus 3n plus 1. We're running out of space here. I allotted myself. And then what I'm going to get is a limit as n goes to infinity of, let's see, 5 over n. I get 11n plus 10, and then I get the 25 over 6n. So the 2 and the 6 would cancel, give me a 3. N squared over n gives me an n, so that's going to be 25n over 3. And then I'm going to get, let's see, 3 and 6 cancel, give a 2 on the bottom, plus 25 halves, and then plus 25 over 6n just times 1. See, that's going to be a limit as n goes to infinity of 5 over n times, let's say I can combine the ends here. 25 thirds plus 11 would be 33 thirds. That would give me 58 thirds n. And let's see, then I have 10 plus 25 halves. 10 is 20 halves, so that's plus 45 halves, plus 25 over 6n. And finally, I'm going to distribute this 5 over n. So then the n's will cancel. 5 times 58 is 250, 290 over 3. I'll get, let's see, 225 over 2n. Whoops. And then I'll get, let's see, 125 over 6n squared. Now, when n goes to infinity, these second two terms are going to go to 0. So I'm just going to end up with 290 over 3 plus 0 plus 0. My answer looks like it's 290 over 3. So this is using a Riemann sum to calculate this. This took a fair amount of time here. I'll just show you the sort of Fundamental Theorem of Calculus way to do this here, because it's much, much simpler, and it's a nice check on these. So really, this integral, what I can do is I can find an antiderivative of x squared minus 3. So an antiderivative of x squared works out to be x cubed over 3. I'm going to add 1. There's really a formula, really our antiderivative of x to the n dx. I go x to the n plus 1 over n plus 1. We should probably have a plus c here, which I'm not using right now, which is c equal to 0. So essentially, if I differentiate x cubed, I get 3x squared. The 3's cancel, and I'm left with my x squared. I'm going to get minus 3x. If you differentiate 3x, you'll get 3. And then the minuses go through. And just evaluate that at 2 and 7. So it's 7. 7 cubed is 49 times 7 is 280 plus 63. That's 343 over 3. So I'm just plugging a 7 cubed over 3 minus 21. And then you subtract, plug in 2 here. So you plug in 7, evaluate this, minus this, evaluate when you plug in 2. So that's minus 8 thirds minus 6. And so let's see, 343 over 3 minus 8 over 3 is going to give you 335 over 3. Minus 21 minus a negative is plus 6. That's minus 15. So that's 335 over 3 minus 45 over 3. That works out to be 290 over 3, which gives us the same answer. Now, question is, why would I do all this stuff in blue when I could do this a little bit in green and it's just sort of much simpler? The answer is you probably wouldn't bother doing this stuff in blue, but the point is just to understand how to do this if you needed to in sort of a more complicated situation. Maybe sort of what's going on underneath will help us understand some applications here, but really this thing in green is probably what we would realistically do down the road. But you can do it either way. Here, just way faster to do the thing in green. Okay, now we want to find the average value of f of x. That's equals x squared minus 3 over the interval 2 to 7. Note the previous question, we calculated this definite integral here to be the 290 over 3. And now if I want to find the average value, essentially what we've got going on is that from 2 to 7 here, the area of this is 290 over 3. One way to think about the average value is I'm looking for some height up here. So this is my average value, so that if I sort of replaced this graph with a rectangle with that height, but with 5, that it'd sort of have the same area. So this looks like it's too high because the area up here, it looks a lot smaller than the area down here. So sort of the area above this red line should equal the area above the red line, but below the curve should equal the area above the curve, but below the red line. This is not drawn to scale, so I don't know that that's particularly useful that it doesn't match here, but it sort of doesn't quite look right. Well, that's our general idea. And so essentially we're building this red rectangle. That red rectangle, the area, we can do this in two ways. One way is, well, we know the area is supposed to be the 290 over 3. Another way is we can just do our area formula for a rectangle. The sort of width down here is 5, and the height should be my average value. Whoops. average value. Well, that just tells me that the average value, really, it should just be 290 over 3 times 1/5. Here. And let's see, this is going to be 58 times 5. Cancel the 5s, and so you get 58 thirds is really your average value of x squared minus 3 when x goes from 2 to 7. Here. Maybe I should put up the general formula here. Is it's generally going to be 1 over b minus a, that's like the 1/5, times the integral from a to b f of x dx. Where this 290 over 3, that's really that integral, but we did that in the previous question. Okay. Next one. Right, so number 4 here, what we're going to do is just work on a summation problem here. So what we get here is we're going to have to do, let's see, a summation k equals 0 to 2n, negative 1 to the k times k cubed. It's probably different strategies to work on here. The one that's going to work here is I'm going to sort of split up this negative 1 to k causes me issues. If that wasn't there, there's a nice formula I could use. But I'm going to sort of split this up into sort of a difference here. Or a sum of differences. So what I'm going to do, let's just write this out. Plug in k equals 0, you get 0 cubed. Note, negative 1 to the 0, that's 1, so that's positive. When I do a k equals 1, negative 1 to the 1 is negative 1 to an odd power, that's a negative, so I'll get actually a minus 1 cubed. And plug in k equals 2, I'll get a plus 2 cubed, minus 3 cubed, plus 4 cubed, minus 5 cubed. And this will keep going on until eventually, one of the last ones I'll get is a plus 2n minus 2 cubed. And then I'll get a minus 2n minus 1 cubed, the last odd. And then finally I'll get a plus 2n cubed. So I just sort of wrote this out. This dot, dot, dot is really using the sigma notation here, although the sigma is more precise here. And so what I'm going to do is I'm going to group these in pairs. So I'm going to take 0 cubed minus 1 cubed, 2 cubed minus 3 cubed, 4 cubed minus 5 cubed, and I'm going to do 2n minus 2 cubed minus 2n minus 1 cubed, and then I sort of have this extra 2n cubed left on the outside. That's okay. So what I'm going to do maybe is think about this. This is a equals 0, a equals 1. I'm going to just do a different indexing variable. I'm going to use a. So this is 2 times a, so 2 times 0 is 0. 2 times 1 is 2. This is a equals 2. 2 times 2 is 4. And I'm going to get, this is a equals n minus 1, because 2 times n minus 1 is 2n minus 2. And so this I can rewrite in sigma notation, but using a as a summation a equals 0 up to the n minus 1. And think about what each of these things are. So this is a, or the first one cubed, actually that's 2a cubed, minus the next one is 2a plus 1 cubed. And then this whole thing, I also have this 2n cubed floating on the outside. Now 2n cubed, that's really just 8n cubed. The 3 exponent distributes to the 2 as well as the n cubed. And now I'm going to do some algebra on the inside here. So the key thing is we got rid of that negative 1 to the k. I'm also going to write the 8n cubed out in front, so I don't have to use these parentheses. So I get a equals 0 to n minus 1. I get 8a cubed minus, now 2a plus 1 cubed. And there's a formula here when I do x plus y cubed. Binomial formula tells me this is x cubed plus 3x squared y plus 3xy squared plus y cubed. Here really our x is 2a, so we get 2a cubed. That's 8a cubed. So let's just write this out in our case. This is 2a cubed plus 3 times 2a squared times the y is just 1 plus 3 times 2a times 1 squared is just 1 plus 1. So I get 8a cubed. 2 squared is 4 times 3 is 12. A squared. 3 times 2 is 6a plus 1. So we get that. Now we just need to simplify down what's inside. The big simplification here is really the 8a cubed and the 8a cubed cancel. And so then what I'm left with, how about a equals 0 to n minus 1? we have a negative 12a squared minus 6a, that negative distributes, minus 1. And so what I get is 8n cubed. I'm just going to split really this summation up into a bunch of different summations. So minus 12, a equals 0 to n minus 1, a squared. Minus 6, summation a equals 0 to n minus 1 of just a. And then just minus 1, or just minus the summation n a equals 0 to n minus 1 of just 1. And really now we've got that. And we can use our summation formulas. So let's just recall here. If we do k equals 1 to n of k, that's n times n plus 1 over 2. And a summation k equals 1 to n of k squared is n times n plus 1 times 2n plus 1 over 6. So we're going to use those. Note we have n's in our formulas, but we have n minus 1's on top here. The zeros here on these two don't matter, because if I do a equals 0, that's 0, and that doesn't affect the sum. So I might as well go a equals 1 to n minus 1. In any case, what I get is 8n cubed minus 12. A squared, I'm going to use this formula here. So I'm going up to n minus 1. So I get it n minus 1. And then the top, the n minus 1 plus 1, that's really an n. And then 2 times n minus 1 is 2n minus 2, but I have to add 1 to that, so that's a 2n minus 1 over 6 minus 6 times the formula for a equals 0 to n minus 1 of a. Again, I can replace the 0 with a 1. And that top is n minus 1. Add 1 more is n, divided by 2. This last one, this is 1 plus 1 plus 1 plus 1. So typically I might be tempted to say that's n minus 1, but here the a equals 0 actually matters. And there's n total terms, so I get a minus n. So now we got rid of the summations. This is really a closed form, although we should really simplify this. And so what we get is 8n cubed. See, the 12 and 6 cancel to give me a 2. So we'll get a plus, no, not plus, minus 2n. n minus 1 times 2n, let's see, it's 2n squared. We get a minus 2n minus n minus 3n. Minus 1 times minus 1 is plus 1. 6 and 2 cancel, give a 3. So I get a minus 3n times n, that's minus 3n squared. Minus 3n times negative 1 is plus 3n. Then we get a minus 1. So I end up with 8n cubed minus 4n cubed plus 6n squared minus 2n minus 3n squared plus 3n minus n is 2n. See, this minus 2n plus 2n cancel. And what we're left with, 8n cubed minus 4n cubed, that's 4n cubed, 6n squared minus 3n squared, that's plus 3n squared. Here. And that does it for this worksheet.